Hello, my name is Mahdi Irfanian and today I'm going to present Chameleon Foundation Models for Fairness over Multi-modal Data Augmentation to enhance coverage of minorities. So first, let's take a look at some news headlines that can help us understand the motivation behind this paper. First one is driverless cars worse at detecting children and darker skinned pedestrians. Second is HP webcam can't recognize African American faces. Third is Google's CEO image search gender bias hasn't really been fixed. Fourth is speech recognition tech is yet another example of bias. And fifth is study finds gender and skin type bias in commercial artificial intelligence system. As you can see, there is this growing awareness toward unfairness of minorities in different ML models. And one of the main reasons of this unfairness is underrepresentation of these minority groups in training data. And there's this growing body of work on detecting lack of coverage of minorities in a data set. But the solution to this, so how can we fix this problem, is still an issue. If we think back, we can say that, okay, we can just collect more data. So this is the first solution. But this solution could be very expensive and sometimes even not feasible. Another solution that researchers have been thinking on is generating synthetic data to simulate the behavior and distribution of the data that we need. So we can add this to our training data set and retrain an ML model, and we'll hopefully have less unfairness toward minorities. There have been extensive research on generating synthetic data for alphanumerical structured dataset. But when it comes to multimodal data, the underrepresentation issues and solution is widely understudied. So that's what we are doing in Chameleon. So our idea is that we can use generative AI to create synthetic data to resolve underrepresentation of minorities. Now let's get formal and define this problem formally. So given a multimodal dataset D with n tuples, and each of these tuples have attributes of interest, the attributes of interest like gender, race, age group, and etc. We can define a subgroup as the Cartesian product of values on a subset of these attributes. So for example, if we have gender, race, and age group, white male could be a subgroup. Even white female preschooler could be a subgroup. So black male, male, female, all of these are our subgroups. And we define the level of subgroup as the number of attributes that we are using to describe that subgroup. So for example, black female has 2, so it's 2. And we call a subgroup a combination if we fill every attribute. So if we have age group, race, and gender, then black, female, preschooler would be one combination. Let's continue. So our goal in Chameleon is to use the foundation model to generate a minimal set of synthetic tuples to resolve inadequate coverage for the most general subgroup. The most general subgroup is the subgroup with smallest level that the coverage of that group is less than threshold. So for example, if we have threshold of 50 and the number of black females in our dataset is 40, then black female is maximal uncovered pattern that we have to fix, but black and female should be covered. If either of these are not covered, then they will be the most general subgroup. Now you can think that, okay, we find this most general subgroup, then we can just pass this to our foundation model and generate the tuple that we need. But there are lots of challenges during this development that we are going to talk and discuss about. So first one is that we have to find a minimal set of synthetic tuples that if we generate these tuples and add them to dataset, the issue of underrepresentation will be gone. And the second one is that we have to preserve the semantic integrity of our dataset. For example, if we think in the context of images, if we have lots of images that are headshots of people, then we can't add people wandering in nature to this dataset because the context doesn't match. We shouldn't add any outlier here. Third is that we have to make sure that the quality of these generated tuples are high enough to be acceptable. We will talk in detail about the quality of generated tuple in the next slides. And the last but not least is the cost effectiveness of repair process. This process of issuing query to foundation models is expensive, and we have to minimize the number of queries that we are issuing to foundation model. So let's take a look at each of these problems in more detail. So for combination problem, what combination to generate? We showed that this problem is NP hard. It's actually shown in the past papers, and we propose a solution, a greedy approximation algorithm for this problem that has logarithmic approximation ratio. For the next problem, for how to detect if a generated tuple is an outlier, we formalize the distribution as embedding, and we find the embedding to represent the underlying distribution of data, and we use one class support vector machine or OCS-VM test to find outliers, to detect outliers and reject them. Third, for the quality evaluation phase, that we say that okay, our metric here is that do generated tuple look realistic in the context of images? Do a human evaluator think that this generated tuple is a realistic image or not? And we model this as a tuple, as a Bernoulli random variable, and our solution to this is that, okay, we ask multiple evaluators and we create a hypothesis testing, a student's t-test, to pass or reject this tuple. The guide tuple selection problem is that, okay, now we have this foundation model that we can issue a query to, and how to generate a good tuple, how to get a good tuple out of this foundation model. And we want to preserve the context. We do not want to generate an outlier, and also we want to have high quality images. Here we can add a guide to the generation process. So instead of relying only on the imagination of foundation model, we can have a guide image that can help foundation model to generate a picture like this guide image. So how can we choose this guide image? This is a problem that we resolve using LinUCB and contextual multi-arm bandits. So the details of all these solutions and problems are in paper. In the interest of time, I have to skip the details, but if you like to know more about the details, please read our paper at VLDB 2024. So let's take a look at the components of Chameleon for image repair. So we have this combination selection component that will identify the underrepresented group given our metric. So it could be representation rate, it could be a threshold for the number of images, whatever that you want. And then we get that. For example, here we get Indian male school-age child. So we need this picture. We choose a guide image. Different policies are available here. We experimented on different policies. You can check that on our paper. So for example, here we choose a white male school-age child. So we have this image. We generate the mask, the parts that foundation model is allowed to change them, and then we pass all three to our foundation model, in this case DALL-E 2. Then we get the generated image, we do the outlier test using OCS-VM and also the quality test. Then if these two tests passes, then we can add this image to our dataset. So that is the overview of Chameleon. In our evaluation, we used 4 datasets: VLDB, Animal 10, UTK face, and also emotion. 3 of them are in realm of images and 1 of them is text. And for our metrics, we have precision, recall, F1 score, the respective disparities, and also the price of fairness, the price that we are paying in performance to gain fairness. And in our baselines, we have without any augmentation, smooth, reveighing, and also as an upper bound and best case scenario, real images augmentation. So, for example, in this experiment for VLDB, we have 3 underrepresented groups: Black, Hispanic, and Middle Eastern. And as you can see, the unfairness for these, the disparity is so high. After repair, you can see that the disparity decreases in all groups and for all measures. And the price of fairness that we are paying for this repair is so low. As you can see, for example, we have a final score of 0.66 using Chameleon, and without augmentation is 0.67. So we are only losing 1%. But in other baselines, we are losing a lot. In the next experiment here for Animal 10 dataset, the results are same as previous one. We are gaining much in fairness and losing a little performance. But another thing that we have here is that we have real images as our baseline. So we have, for underrepresented groups, you can see that the performance of Chameleon and adding real images are so similar. So it shows that Chameleon have generated high quality and in the same context, not an outlier, and added that to dataset that if we do that with real images, we are going to gain same performance. In the next experiment, what we have here is that we change the modality from images to text to show the flexibility and scalability of Chameleon, and we change the component of combination selection problem from threshold based coverage to representation rate. So we have three underrepresented group with 10% representation rate here: fear, love, and surprise. So these three emotions are underrepresented in our data set, and we are going to generate synthetic tuples to increase these numbers. As you can see, we gain about 15 to 20% improvement in F1 score, and also we thought about this idea of only using synthetic data. So what happens if we only have synthetic data for these two emotions, for example, surprise and love? And as you can see, we get a F1 score of 0.1 and 0.2 only from synthetic data, and it shows and proves to us the importance of not adding any outlier and following the distribution, being in the same context as your training data, because here we don't have any idea of the distribution, and you can see that the performance couldn't jump to 60-70%. And as you can see, the unfairness for all groups decreases using Chameleon. Okay, just to wrap this presentation up, we introduced Chameleon, a system for fairness over data augmentation aimed at reducing minority group underrepresentation. And we use the advancement in foundation model to repair data with minimal synthetic data addition. Also, we ensure that the augmentation, the tuples that we generate, are high quality, and we don't add any outlier to our data set. And we showed that it could help with the reduction in unfairness in downstream ML tests. Please feel free to send me an email and ask any question if you have. Thank you for attending this presentation. I hope you enjoyed.